Chapter 6, the normal distribution. A continuous random variable is a variable which can take any real value within a certain range. We usually denote random variables by a capital letter such as x, and individual measurements of this variable are denoted by the corresponding lowercase letter such as little x. For a continuous variable x, the probability that x is exactly equal to a particular value is 0. So, the probability that big X, is equal to a or a particular value is 0 for all possible a or all particular values. For example, the probability that an egg will weigh exactly 72.9 grams is 0. And we talked about this when we talked about continuous variables. If you put it on a more exact scale, you might get a better reading even though it's the same egg. If you're to weigh an egg on scales that weigh to the nearest 0.1 gram, a reading of 72.9 grams means the weight lies somewhere between 72.85 and 72.95, okay, because it rounded to the nearest 0.1 gram. No matter how accurate your scales are, you can only ever know the weight of an egg within a range. So for a continuous variable, we can only talk about the probability that an event lies within an interval between a and b, and they can say it's equal to, or just between a and b but not equal to, or equal to one and not the other. And bottom line, all of those probabilities will always be the same because it's the same amount in the interval. Now let's review what we know about distributions. Data can be distributed or spread out in different ways. We could have it spread out more on the left, so then it's left skewed, or spread out more on the right, so most of the data is on the left side with the outliers on the right, so that's right skewed, or it could be completely jumbled up. But there are many, many cases where the data tends to be around a central value with no bias left or right, and it gets close to a normal distribution like this. So that's the bell curve everybody is always talking about. This is one of the most widely used distributions for a continuous random variable, and it often occurs naturally. All normal distributions have the same general bell curve, but the exact location and shape of the curve is determined by the mean and the standard deviation. For example, we can say that the height of trees in a park is normally distributed with a mean of 10 and a standard deviation of 3 meters. So what we would do is we would take 10 and add 3 to it, so 13, 16, 19, to get our markings for 3 standard deviations above the mean and similarly below. And you can see that it's kind of a nice spread out bell curve. At the same time, we could have another normal distribution that's measuring the time it takes Sean to get to school. On average, it takes 15 minutes with a standard deviation of 1. Because his standard deviation is so small, the variability is small and the curve is taller. Notice that the curve is always symmetric about the vertical line x equals the mean, which is either going to be x bar if you have sample data, or mu if you have population data or we're able to take a census. When distributions are unimodal and symmetric, they can often be modeled by a normal curve. Technically, the normal curve is a mathematical function that extends from negative infinity to positive infinity. Thus, a normal curve will never model a data set perfectly, and data sets should be described as approximately normal, never normal. So there's that thing, approximately again, where you'll get taken from a E to a P on a free response question. When we use a mathematical function to describe a distribution of real data, we call the function a model. The normal model is centered at the mean mu with a standard deviation of sigma. And this is how they write it. Okay, so for example, with the egg thing we were talking about before, we say x equals the egg weight, or the variable we're talking about, and then x is approximately normally distributed. The mean goes here, and the standard deviation goes here. So that's the shorthand. When graphing a normal distribution, the inflection points, so where the graph goes from down to up, are located at one standard deviation above and below the mean. We use Greek letters to denote that these values are not calculated from the data in a sample. They are either calculated from the entire population or they are assumed values to help solve problems. Numbers like these are called parameters, for example, mu and sigma. In contrast, summaries of data from samples are called statistics and are represented with non-Greek letters such as x bar and s. Now, the good thing about a normal distribution is that the amount of the population, or the percent of the population between standard deviations, is fairly constant. Now, we often say that there are 68% between one standard deviation plus and minus, 95% two standard deviations around the mean, and 99.7 three standard deviations. But if you wanted to go out one more or two more decimals, you could get these values. Notice that they are perfectly symmetric. So here's one standard deviation, which is about 68%. Two standard deviations from the mean. Add those pieces up. You'd get about 95% of your curve. Then three standard deviations from the mean. You have almost your whole curve, 99.7. If you wanted to go four standard deviations out, you could pick up another 0.13. But remember, this actually goes on forever. It's just an infinitesimal amount of the curve under there. For this homework, if the probability you're looking at is between two actual standard deviation points, I want you to use all four sig figs, or two decimal places. That is how the key is written, and if you don't do it for homework 1, you will miss points. Drawing a normal curve is really as simple as going like this, but if you wanted to be super accurate, you could follow this description. It says start with the axis and label the mean and three standard deviations. So I drew a line and space three standard deviations evenly apart. Then down the middle, I found 50% and then 60. And the one standard deviation mark is at the 60% of the height of the mean. Two standard deviation marks, this I didn't do a very good job, is a 1/8 of the height, and then the curve follows down below. But really that level of accuracy is never necessary. Let's do some simple examples. Suppose that the birth weight of newborn babies are approximately normal with a mean of 7.6 and a standard deviation of 1.3 pounds. The very first thing I'd want to do is to go ahead and define my variables and my distribution. So I put it in that shorthand. Then I'm going to draw a curve starting from my mean and then adding 1.3 to each value and subtracting. So now we've sketched a normal curve with the correct scale, and even if I didn't ask for that, you'd want to do that. And now let's answer some questions. It says, what percentage of babies will weigh less than 8.9? Okay, and I had to show the answer to read the question. I think it's best if you draw a quick curve for every problem. If you want to draw one curve for every couple of problems, that is fine, but you need to fill it in. So it says, what percentage of babies will weigh less than 8.9 pounds? Go to 8.9. Well, we have this 50% plus this 34.13, and we have 84.13%. I am expecting this level of accuracy on your homework and not from the calculator. Next question, what percentage of babies will weigh more than 8.9 pounds? So we're going this direction. We could add up all three of these spots or use the complement and just do 100 minus the answer from the previous problem, and we get 15.87. Number 4 says what percentage will weigh more than 5 pounds? So we're at 5 pounds, and we're going to color. The good thing about the pictures is if you get a weird answer, so if let's say we got an answer here that was less than 50%, we'd know that wasn't correct because our graph is definitely more than 50%. Anyway, to get it, we would add up, well, we could add up all of these, this one, this one, this one, this one, this one, and this one, going back to our curve here, and adding up 13.59 plus 34 plus 1.13, blah, 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 blah. Or, again, knowing that the whole curve is 100, or 1, we could just add up this one and this one, 2.15 and 0.13. That gives a total of 2.28. 1 minus 2.28, and we have 97.72%. For number 5, what percentage will be between 6.3 and 10.2 pounds? 6.3, 10.2, let's see, 34.13 plus 34.13 plus 13 point something, 13.59, and we have a total, add up the 50 plus 34.13 plus 13.59, and we have a total of 99.72%. Again, you could do this in decimals or as percents, just don't confuse the two. Then number 6 says, between which two weights will the middle 95% of babies be? Well, that is 2 standard deviations, 5 and 10.2. Finally, it says, what proportion of babies weigh less than 8? So I go on here and I have a problem because 8 is not on one of my standard deviation lines. And I want less than 8. So I've got 50% here plus this proportion. Well, if I wanted to, I could estimate it. So let's see. We know we already have 50%. So what we really need to focus on is this little piece right here. Let's look at it this way. We know from 7.6 on, that's 50% or 0.50. And we're trying to find the part from 8. So if we did 8 minus 7.6, we realize that there's 0.4 in this little area. Okay, well, how much is 0.4 of this standard deviation? That standard deviation is 1.3 based off the story problem. So if you did 0.4 divided by 1.3, you'd get 0.31. Okay, and that's a percent. That's how much of the curve is between 7.6 and 8. So then to find out my total, we would say, okay, we have the, okay, so we know that from 7.6 to 8.9, we have 34.13% of the curve, but we only want this little piece right here, which we found out is 0.31% of that red box. So times them together, and we realize that of the whole curve, we have 10.5% in this orange section. So to find my total, we're going to take the 50% here, add it to the orange section that was 10.5%, and the proportion of babies weighing less than 8 pounds is 60.5%. Well, that is miserable, and we don't want to do that all the time. So we can use a z-table and a z-score. And let's look at this example. So let's look at the same story problem, but go ahead and standardize it. So we're going to use our z-score from the first unit, which is every value minus the average divided by the standard deviation. And we were trying to find the proportion of babies that weigh less than 8 pounds, like we did up here. So we do 8 minus 7.6, oh look, which is what we did here, divide by 1.3, and our z-score is 0.31. Okay, and that is what we did over here when we just kind of logicked it through. What the z-score means, and I said what the z-score means again, is that we've turned our mean of 7.6 into 0. We have one standard deviation of 1, and this 0.31 is right here. 2 standard deviations would be 2, 3 standards would be 3, and by standardizing it, we could use a table to find our answer. Remember, they didn't have calculators way back when, and so they needed to have a way to convert everything to one set of units, and then they could tell you all the probabilities between all the possible combinations. So again, the z-score is between 0 and 1, so we know at least 50% weigh less than 7.6 pounds. We also know that at most 84% weigh less than 8.9 pounds, because that was the 50 plus the 34 right here. Thus, we know our answer has to be between 50 and 84, which we found at 60.5. To be more precise, we can use the standard normal table, which gives normal percentiles for the standard normal curve, which is the normal distribution with a mean of 0 and a standard deviation of 1, which I just talked about. Therefore, whenever we standardize a value from a normal distribution, i.e. calculated z-score, we can use the standard normal distribution to find what proportion of values would be less than or equal to the original value. The z-score only goes less than or equal. It only goes this direction on the curve. For homework number 1, you have to either use the values right here because your problems landed on the standard deviation, or the z-table. If you use your calculator and you already know how to use it, you will miss all the problems for homework number 1.